Hi, everyone, and a warm welcome to our Human-centric Innovation webinar, part of Queen Mary's Breakthrough in AI series. My name is Maria, and I'm Marketing Manager in the Faculty of Humanities and Social Sciences. And I'm delighted to be here with you today, joined by two celebrated academics, Professor Pat Healey and Dr. Lorenzo Jamone. I'm also joined by our host, biomedical engineering final year student Kameron, who will lead today's discussion. Before we get actually started, I just wanted to quickly run over some housekeeping information. We will be with you today between 45 minutes to an hour, depending on how many questions we get. So if any questions spring to your mind while the session is ongoing, please use the Q&A section of this webinar, and we will respond to the questions during the Q&A portion of the session towards the end. We will try to answer as many questions as possible during the talk. And please also note that this webinar is being recorded, and you will be able to view it on demand by yourself or in the future viewers. You will be sent the recording via email should you want to access it again. Now I will be handing over to our student host and budding AI expert, Kameron, to start the talk. Thank you.
Thank you, Maria. Good afternoon, everyone. Very excited to have you today. So as Maria mentioned, my name is Kameron Young, and I'm a final year biomedical engineering student here at Queen Mary. I love learning languages, both lingual and programming based, and thanks to that, I speak English, Spanish, and have experience with Python and C#. I recently started a podcast called Kameron's Lab Dive In to give students insights into the world of STEM. I interview industry professionals just like our guests here today. So without further ado, please allow me to introduce them. So I'll start off with you, Professor Pat Healey. He is our first panelist and a renowned figure in the world of human interaction and cognitive science. He's the head of cognitive science research group here at Queen Mary and a former Turing Fellow. He's also now the head of the new Center for Human-centered Computing and formerly the senior researcher in residence at the Digital Catapult. His work primarily focuses on human-human interaction and developing technologies for improved communication. Professor Healey's current projects include adaptive learning technologies that can tailor communication in real time, analysis of physical cues for collaborative robotics, and working on new environments for communication in social virtual realities like the metaverse. Our second panelist, Dr. Lorenzo Jamone, is a senior lecturer in robotics at Queen Mary and the director of the CRISP group. CRISP, or Cognitive Robotics and Intelligent Systems for the People, focuses on developing robots to enhance human life and understand cognition. The focus for the robots is to use their hands intelligently as humans do. As a Turing Fellow, his research is rooted in cognitive robotics, aiming to create intelligent robots inspired by human cognition. His work covers various areas, including dexterous manipulation, visuo-haptic perception, and human-robot interaction, with the ultimate goal of integrating robots effectively into human society. Now, if that's not exciting to you guys, I don't know what will be. So I'm very excited to speak with you both today. Thank you for joining us. So I'll just get off and get started with you, Dr. Lorenzo. So I wanted to ask if you could give us a brief overview of what's the difference between cognitive robotics and traditional robotics.
Yeah, thank you, Kameron, for the introduction. Hi, everybody. Pleasure to be here. Right, so cognitive robotics, which is my main area of research and is also one of the modules that I teach here at Queen Mary. This is how I define it. Is this, let's say, this science, this discipline that has two objectives. One objective is to take inspiration from biology and looking at human intelligence and animal intelligence, and take inspiration from that to create better robotic systems. Robots that can help us in our everyday life, in industry, in hazardous environment, anywhere where we want to have robots that are more intelligent. But at the same time, using robotic technologies and computational modeling to better understand human intelligence. So somehow to be able to create this loop where the disciplines, the cognitive science disciplines like psychology, neuroscience, cognitive science, they can create inspiration for robotics, but then robotics can also contribute to better understand human intelligence and the human brain. And this is the main philosophy behind cognitive robotics, which I think it's very exciting. At least it's very exciting for me.
I agree. And speaking of this loop between understanding human communication and also understanding robotics, how would you say that understanding our cognition contributes to the advancement in such robotics?
Yeah, so, well, you also asked me first, like, what is the difference between cognitive robotics and traditional robotics? So in general, the objective of robotics will always to create robots, create machines that they can do work for us, basically. Things that we don't want to do, things that are boring for us, things that are dangerous for us to do. We want to create machines that will do those things, and they will help us to do those things better, right? That's the main objective of robotics in general. Now, traditionally, robotics, the way it has been included in our society was to basically, so mostly it was in factories and in environments that we call structured environments. So environments that somehow are made easier so that the robot could do things there. For example, if you have to create, like, to manufacture a car, and you have to manipulate all the different parts of the car in a factory, you will put those parts on precise positions, and you will know everything about those different parts. And then after you know that, you write mathematical models and computer programs, and the robot will execute the same action over and over. For example, picking a part of the car in one place and putting it somewhere else. And this is like the repetition of a very simple kind of action, right? And for that, the robotics has been great in the past, 60 years, and a lot of useful uses. Now, when you want to bring those technologies in environments that are less structured, so for example, imagine a kitchen, whatever kitchen where you want to cook some food, or an hospital where you have patients there, or a field where you are harvesting fruits or vegetables, right? So any environment which is a bit more unstructured, where you cannot precisely define where things are because things change and move around, and there are people as well, then it becomes much more difficult to put robots there. We still don't have the technology that will enable us to have autonomous robots that are able to understand the situation and do things over there. And so intelligent robots or cognitive robots have the potential to have more autonomy and to be able to interact in those situations. And that's why we take inspiration from humans, because that's the best examples we have of agents that are able to do these things in this type of environments. And so from, let's say, one main objective in that sense is to take inspiration from our intelligence and our autonomy, our perception, to create these things in robots so that they can operate in those environments. And then there is an additional aspect, which is if you have robots that will do things in a way that is somehow similar to the way in which humans do things, it will be easier for humans to cooperate with such robots, because it will be easier for humans to understand and predict what the robot is going to do in different situations. And this could be, when we collaborate with other people, like human collaboration, communication, we always have expectation of what the other person is going to do, how he's going to do it, how the body movements will prompt a certain action or a certain behavior, right? And so somehow, if we can have robots that behave in a similar way, then it will be easier for humans to cooperate with this type of robots. So that's at least another aspect or another perspective to see why taking inspiration from humans to make robots can be beneficial for having robots that help us in our daily activities.
That's very fascinating. And it also links into your own research, Professor Healey, because you're also doing cognitive robotics. So could you talk to us a little bit about how you've noticed that there's a difference between the way that people interact with each other versus how the robots maybe interact with each other or interact with humans? What have you noticed between those kind of interactions?
Well, it's really interesting. So it's usually an interesting problem that it sets you when you try to think about how you would build something, to do even something quite simple like handing a pen to someone. So it seems kind of straightforward, until you try to engineer a system to do it. And then you find that actually there's a really complicated set of cues and interdependencies when human beings hand over a pen. So there'll be moments of eye contact. There'll be points at which, as the pen is moving, the hand moves to grab it. The hand shape itself tells you something about what they're going to do, whether they're going to put it up or put it down. Also, there's the kind of joint, something Lorenzo thinks about quite a lot, the pressure, how you sense the degree of pressure and when somebody's going to let go. And then perhaps you'll do something like smile afterwards to show that you've completed the task. Robots, thinking about getting a robot to do that makes you look very closely at what people are actually doing. And then you have to think about what kinds of sensors you need, what kinds of force sensors, what kinds of ways of communicating things like task initiation, task completion, all of those cues that we find very, it's transparent to us. We don't think about it. But actually, there's very fine-grained coordination going on.
Sounds like a lot of subtle communication cues that you have to pay attention to as well. And speaking of which, when I was speaking with you previously on email, Dr. Professor Healey, you mentioned about making robots blush, which I would very much like to learn a little bit more about. And I feel like people might find that interesting. So would you mind explaining what you meant by that?
This is work with Simi Park on a PhD recently. Lorenzo was helping with that as well. So the point was really to think about the fact that robots really, although we have these exciting images of humanoid robots that can interact and walk around and so on, they're not really anywhere near being competent at those tasks at the moment. And maybe they never will. I mean, it's possible that there will never be enough reasons to build what would be a very expensive and very difficult to engineer robot that could actually mimic a human. So maybe you're faced with the fact that you won't always perform properly. Well, if you think about that, neither do people. And what people do when things go wrong, one of the things they do is they blush. And blushing is really interesting, right? Because it shows that you recognize that you've done something wrong, or failed to do the right thing in a certain circumstance. But it also elicits sympathy. So you spill a cup of coffee, you apologize, you blush slightly, and then people will typically normally help you clean up or whatever. And that's a really interesting proposition for robotics, because one of the things you might want to do is get people to help train a robot in situ, doing tasks around, your quite complicated kitchen environment, where all sorts of things are very strange and in strange places, and there's a lot of learning to do. And if you can enlist the people who are using the robot to help you train the robot, that's really quite a positive thing. So we just got very interested in, how could we use this? Could we think about ways in which a robot could blush to signal that it recognizes it's done something incorrectly, and then elicit the help of other people in putting that right. And that's kind of, when people think about robot facial expressions, they normally think about things like smiles or nods. But this is a different, a really different class of expressions, blushing and embarrassment.
Wow. I think that does kind of lead into what I wanted to ask you a little bit later, Dr. Lorenzo, so about just little subtle things that can make us a little bit more emotional, I guess, towards the robot, having that different human connection that we would have with each other, getting people to have it with robots. So I want to ask a little bit more about things like, for example, tactile sensing. So when you're able to, when the robot can tell what it's holding or what it's seeing in that kind of way, how would you link that into your robotics? And also, why do you think that's so important?
Yeah, I mean, one of the aspect that we deal with in our research group, maybe the kind of central research question we deal with, I call it the intelligence of the hands. I think in general, like our hands, they're so intelligent. And if we look at our brain, there is a large portion of our brain which is dedicated to receiving sensory information from our hands and controlling the movement of our hands. A very large portion of our brain is fully dedicated to that. And it makes sense because, I mean, that's the main way we interact with the outside world. We do things with objects all of the time. So our brain is fully dedicated to that. So it's a very interesting topic to study, especially because then when you try to do those things in a robot, you understand that I made example before, the difference between a very structured environment, the industrial environment, and any other environment. If you want to simply pick an object, it's very easy to do it in a very structured environment where you know exactly where the object is and you know exactly that the object is going to be rigid, for example. But if you have to pick a strawberry from a plant, then you don't know exactly what the stiffness of that strawberry is going to be. You don't know exactly where it is, etc. So it becomes much more complex. And when you try to do it with a robot, you realize that it's so difficult. For us, it's so easy. It doesn't mean that it's actually easy. It's easy because our brain is using a lot of energy and computation to do those things. So it's a very interesting problem to study, and a big component of that is the sense of touch, of course, which of course we have it in humans. We have it on our hands, and it's very important to manipulate objects and to gather information about objects. If you want to know if something is hard or soft, you will squeeze it, and you will use your movements in combination with your tactile sensing. But then we have the sense of touch is on all our skin, right? It covers our entire body. And so, for example, we use it also a lot to communicate things to people. I mean, physical touch is a very important way in which we communicate with the people, we interact with the people. And I mean, we know all very well, we passed through a few years in which during COVID, during the worst times of COVID, it was very difficult for us to have this physical connection, and everybody missed it terribly, right? So there are also a lot of studies that show how that affected many people in stronger ways, right? So of course, if we could have also robots that not only have sensors, tactile sensor in their hands, but also in the rest of the body, and there are some people working on that, we could have another way for robot to interact physically and socially with people, so that can be a very interesting additional modalities. I was watching just the other day a video and an interview from colleagues of mine in Italy that they're working with this cute humanoid robot that is covered with tactile sensors, and they were showing like a demonstration in which person was touching the arm of the robot and kind of caressing the robot, and the robot smiling in response. And that was just the demonstration, but it could prompt to, applications, for example, in elderly care, healthcare, or where you want to have a companion robot that is that somehow alleviates some of the work that people have to do to care about other people, and that is needed a lot. And I mean, we know, for example, just from the example of NHS in the UK, but any health system in the world is facing problems with the lack of people that can do this type of jobs. So to have machines that can provide not only physical help but also this kind of social help, it's very useful. It's very interesting. There is also another example in Japan since many years now, this robot in the shape of a seal, like animal, and that you can pet. Basically, it's a robot pet, and they used it a lot in healthcare, and also, for example, with children with different stages of autism spectrum disorders. And it shows that it's really beneficial for many of these healthcare situations. So yeah, there are many examples and quite exciting, I think.
Yeah, I agree. Very exciting. I think it's really cool to think of the fact that we're training robots to be able to better take care of us later on, and I think that's really interesting as well. But from what you both have been saying, it kind of sounds like like you're raising a robot in a way, like almost like raising a child. So just teaching them little things, learning how they learn. Could you talk maybe a little bit more about how you teach a robot to learn in that way? Maybe Professor Healey, if you wouldn't mind explaining a little bit more, like when you're teaching a robot to learn, what kind of systems would you employ? And I know that's really a broad question, but if you could talk about it in a high level way, I would be really happy.
No, I think it's just a question for Lorenzo, really. He's much more expert than I am on robot learning.
Yeah, I mean, there are many ways in which you can do it. So let's say maybe two major ways are, one is kind of autonomous learning. So the idea that the robot, similarly to what a baby does, it will start to explore and touch the objects and look around, and with time develop the connection between what you are doing and what you're seeing, what you're touching and what you're doing, and then building these internal models that will enable you to later on do things that will generate those sensory perceptions that you're waiting for, right? So if I want to tap and if I want to generate the movement of an object, I know that if I tap it, the object will move, right? And but then there are other ways. I mean, in fact, there are all these different ways in which kids learn. Like kids, they learn by themselves. If you put a young kid in a room full of toys, they will start playing around and moving things around and learning. But they will also imitate, right? They will imitate the parents, the other peers, the friends. They will look at what they're doing and try to imitate. And that is done in robotics. There is a big field of imitation learning. So robots learning from looking at humans. And then there is another way, which is doesn't really exist much in the human domain, but it's very useful in robots, is that you can use a technique called teleoperation. Teleoperation is where you basically, a human user will use some kind of device to move a remote robot. So you have a robot somewhere else and the person is in another location, and they can use a device that could be a joystick or a controller, or it can be another small robot that you move. And the movements you do are replicated by the other robot. And so in that way, you can teach a robot how to do certain things. And so these are some of the techniques that we use.
Oh, that sounds really cool, especially the teleoperating side of it. It kind of reminds me of telesurgery from a biomedical engineering student. I had to bring it up at least once. But I also wanted to ask you, Professor Healey, back to the communication side. One of the papers that you did was titled Human-like Communication, and it was based on the challenge set by Alan Turing at about 1950, I want to say. So I wanted to ask if you've seen, since then, has the technology changed, and do you think it's still a challenge for us to make robots have this kind of human-like communication? I know you mentioned that it might be kind of far off, but I wanted to ask if you could expand on that a little bit more.
Yeah, I think it is still quite far off. I don't think there's any reason why it couldn't ever get there. It's just, I think the challenge is quite a lot bigger than people think. So like one example I came across recently in work by some people in Holland, Honk and Holla, but they were looking at blinks. Blinks are it's one of the most rapid movements you can make. It's just a few hundred milliseconds. And it turns out in conversation, they're a systematic cue. So if somebody blinks quickly, they're kind of encouraging you to keep talking. It's like positive feedback. But if they blink for a bit longer, you interpret it, not consciously, you just automatically interpret it as a sign it should say less. So there's this tiny little cue that, people have not really thought about very carefully. It's all about the pragmatics of the communication and so on. And we're just very far from engineering those kinds of abilities into robots. Of course, you could, but I think there's two sides to this. One is that we don't yet really fully understand enough about how human communication works. It's like a very complicated dance that we're doing all the time. There's a lot more work on verbal than there is on non-verbal communication, although there is a lot on non-verbal, but we're still really discovering very basic things. So yeah, I think it's quite far off, and I think one of the things we need to do is really exploit the social science much more effectively as a way of informing robot development.
I agree. It's more of an interdisciplinary approach. That sounds really exciting as well. But could I also could I also ask a little bit more about the digital side of things? So taking the things that you're learning from robotics into more of a social virtual reality. So like you mentioned the metaverse as well. So could you talk about how your research maybe applies to the more digital kind of side as well?
Yeah, so the really big advances in AI have happened mainly because that we've had a lot of text data available.
Mm.
So, the amount of language in texts that you can access and then learn from has just exploded exponentially. But it's really obvious that the thing about robotics and the thing about human communication is it's embodied.
Mm.
And that kind of, the access to that hasn't been there. We don't have huge data sets of people interacting. We've got some videos, there are some videos and stuff, but we don't have lots of it. But that's all going to change. So the way that social virtual reality and the metaverse is developing, because you've got a headset on and maybe gloves or some kind of motion detector, all of your nonverbal communication is immediately available as data. And that's just a situation we haven't been in before. So, I would expect there'll be another big step up in the ability of AI to deal with all of that nonverbal stuff. And it's quite interesting to think about the Turing test, actually, because the Turing test, when it was devised, it was essentially typing text messages and then waiting for a text message to come back and then typing another one. So it's strictly alternating text-only interaction. And that's the sort of, I think that test has been passed in some ways by some machines. But in general, that's not really how we communicate. We do something very much more multimodal. Hands and faces and eyes move all the time, not just the speakers. Like as I'm speaking, I can see that you're giving me little nods or smiles or whatever as feedback. All of that's really important to the way I talk. I need to get the real-time feedback to be able to respond appropriately.
And we interrupt each other as well.
Yeah, exactly.
Yes.
It's kind of like it's like back in COVID when we were all kind of quiet, like for the online meetings and things, with the camera on versus the camera off. So it's definitely having that kind of feedback is important.
Yeah. So, I think we're just on the edge of all of that, really. But the data is going to be available, and there's just a big opportunity.
And then speaking of like more physical cues, so like you mentioned, the feedback that you get from people smiling at you or people just kind of interacting with you non-verbally, does that also link to more haptic feedback as well? So Dr. Lorenzo, if I could bring you in about some of your research is on visual haptic perception. I wanted to ask if you wouldn't mind explaining, first of all, what that is for those of us that may not know, and then how that kind of links into your research into cognitive robotics.
Yeah. Haptics, there are a couple of maybe some different definitions around, but typically by haptic, we consider the combination of tactile and movements. Anytime in our own sensations where we combine touch and movements, we talk about haptics. Then in the technology fields, a lot of times when we talk about haptics, we talk about haptic feedback, which is, let's say, how a human person can receive some stimulation, for example, on the hands, that will render some tactile stimuli. So, for example, the example of haptic feedback could be I am interacting with some virtual reality, and in the virtual reality, I'm touching an object. So the avatar is touching an object, and the physical person on the other side, they will feel that on their own skin, right? So that's what we call haptic feedback. And for robotics, that's very important for what I mentioned earlier, which is teleoperation. So if you think of interacting with a virtual avatar, but it's quite similar to interacting with a remote robot, right? So basically, in teleoperation, we move a remote robot, and it's very useful if when the remote robot touches something, you operator, you feel it, right? You can feel it as a force acting on your hand, for example, that kind of blocks your movement in one direction if the robot is hitting a wall, for example. Or you can feel it on your fingertips or on your fingers, on your skin. If the robot touches something, you have that feeling back. Some of the experiments that we have done in that sense, they show that other source of information, of course, is visual feedback. You can look at the robot may have a camera, and you may look at that video feed to get a feeling of what is the robot doing. And typically, the visual feedback is very useful to do many things. If you have the visual feedback and you don't have this haptic feedback, in many cases, you are still able to do things with a remote robot, but it's much more tiring for the human operator. It's less natural, and it's you have to use a lot more of a kind of mental effort. You get exhausted after 20 minutes of doing things. While on the other hand, if you have this haptic feedback, things become much more natural and therefore easier to do, especially if you're going to do it for a long time. Which in fact is then the same thing that we see in experiments that are done on people on the importance of the sense of touch when we manipulate objects. There are some old experiments that they anesthetize the fingertips of people to remove the sense of touch, basically temporarily. And there is one famous task of a person trying to light a match with the fingers anesthetized. And they can do it only by using vision without the sense of touch, but it takes like ages. So you can see this video of this person like really struggling to pick up the match and to apply the correct amount of force to light it up. They do it, but it takes 10 minutes or something, right? Something that they will do in 1 second, right? So it shows how important the sense of touch is directly when we do things, but also as haptic feedback when we interact with something remote. And of course, I mentioned this teleoperation, which for robotic is very important. But similar thing happen if you interact with the virtual reality, right? And then the other aspect, which is interesting, people I think now are start talking about tactile internet. So the idea that you can so typically we interact with the internet, for example, mainly through visual feedback, right? You go on a web page, you scroll, imagine the catalog of, an online supermarket, and you want to buy some fruits or some vegetables and you look at them, right? Or you want to buy clothes and you look at them. What if you can actually touch them remotely, right? So similar technologies can be used for that you interact with the web pages where you have different type of, clothes, fabrics, shoes, bags, whatever you want to buy. And you can see them, but you can also touch them and feel the texture, for example. How does this T-shirt feels? Or, is this mango ripe or not? Otherwise, I won't buy. So this is like still a bit futuristic, but this is the type of technologies that, depending on different reason and whether there's going to be investments or not, it could become a reality relatively soon, at least in some context.
No, in fact, I just want to follow up about the social touch stuff as well, because it's so important. So the sense of touch can comfort people, reduce their stress levels, make them feel less socially excluded. It has to be specifically soft touch, actually. There's two kinds of touch that we detect. I think the most striking example is the experiments done on the brain responses to pain. And if you're holding hands with a friend or a partner, just holding hands, the brain response to pain stimulus is substantially reduced. So it actually can mitigate physical pain. Just sort of illustrates the strength of the effects.
Wow. I think I hadn't really thought of how just that sense of touch also helps with, like you mentioned, this like little pain management as well. It's really interesting to learn how we communicate, and that sense of touch really, it all links together. Very interdisciplinary, as you both mentioned. Just for students that are more interested in the cross-interdisciplinary approach of your work, could you suggest ways that they could maybe get involved in this research into like linguistics, cognitive, this like haptic feedback? How do they get involved in that, especially at Queen Mary? If you want to explain a little bit more.
Yeah, can I jump in? So I mean, for what I can say, for example, Queen Mary offers different master programs the two I can mention now is Mastering AI and Mastering Robotics. So Advanced Robotics probably will change name into Master Robotics and AI, because that's in fact what we offer. And students who are joining those courses, those programs, they have different modules. I mentioned one, which is cognitive robotics, the one I teach, and I definitely give a lot of these examples of how to use. So it's a really multidisciplinary module where I give example from psychology to robotics and the connection of it. In fact, for example, within that module, half of the module is about the students doing a small individual project where they take a specific idea from psychology about some human behaviors. They make a computational model of it that could go into a robot. And so they try firsthand how to really take these ideas from psychology, neuroscience, and implement them in a robot so that we can achieve ideally those two objectives that I mentioned in the beginning, having robots that are more useful really for us, but also use that as a tool to understand more. So to kind of prove maybe some of the theories from psychology. Because if you get a theory from psychology of the way in which we communicate or the way in which we manipulate objects, whatever, and then you implement that in a robot and you try it out, then I'm simplifying a bit, but if it works on the robot, you can say, oh, okay, so maybe that idea from psychology is probably true. If you see that the robot behaves in ways that are similar to what is observed in human, you can say, oh yeah, maybe this theory actually it's supported by these experiments that we are doing. Or on the other hand, if it doesn't, maybe that will prompt some different studies that they can do in psychology to look at people in another, with another perspective and say, oh, let me try this other experiment in psychology or neuroscience to verify whether this is actually what's happening, or maybe it's a little bit different, right? And so we give students the chance in a limited, scope, but to understand what this process could be. And then on top of that, they have actually an extended research project, which is 50% of their time overall over the year. And that could be in robotics, it could be in AI, it could be in combination with the computer vision, with the natural language processing, all of the other things that our researchers do in the departments. Yeah.
I think that also comes back to the loop that you both mentioned before of like looking at how humans interact and then applying that to the robots and then applying what the robots do back to the humans. So definitely a nice little loop to come back to. Professor Healy, I'm going to bring you back in. So I would like to ask a little bit more about one of your most recent publications. It was called Power and Vulnerability, Managing Sensitive Language in Organizational Communication. So just speaking about how the different types of communication we've been talking about, I wanted to ask if it's more like what kind of things you've noticed about how, for example, positions of power and how they affect the use of language in workplace communication. If you could talk more about that, I think that links to AI as well.
Yeah, it does. So the basic finding from that paper is that in a very big organization, big engineering organization, if you look at the emails that the managers write and the emails that the members of the groups that they manage are in, you see this very clear difference in the use of any kind of sensitive words. So words that might refer to ethnicity or religion or politics, they're a much lower usage. And that seems to be very much about the role they're in. So the fact that they are, their emails are going to multiple people, that they might ultimately be held to account. I mean, I keep thinking about the recent revelations of the COVID inquiry, where people had their emails and their text messages scrutinized in a level of detail that they probably never imagined would happen. And I think it's that kind of thing that, people in more powerful positions, although there is a stereotype that they tend to be less inhibited and might, say just speak inappropriately more often. Actually, it's the other way around. That because these people are more vulnerable to criticism, they use potentially sensitive language less.
And how do you think that would apply to robotics? Just like as we build up that communication for robots, do you think that there will eventually be I guess, the hierarchy in the way that robots speak as well?
I think what it points to is the fact that we've got to be really sensitive to context.
Mm.
So I swear most often with my closest friends, right? And it's not really abusive. I mean, it's like it's a joke and it's friendly, and it shows that we're all aligned and affiliated with each other. But I wouldn't speak the same way in an email. I just wouldn't, right? And I think that's being really clever about understanding what those contexts are and what's appropriate in some and not in others is a really interesting challenge for AI, because language models tend to be, very big, very generic. They don't really discriminate who they're talking to or what the situation is. So I think that, that's a very interesting challenge.
And then just a little bit of a question on the other hand. So one of the things that a lot of people notice when they're speaking with different AI, or just at least working with different AI models, is this implementation of things like bias, for example. So how would, I guess, you deal with that when you're dealing with communication for robotics? I know a lot of it is like nonverbal, but how do you deal with the implementation of bias, for example, into your models? Hopefully there isn't it, but some things can be.
Is that for me or for Lorenzo?
I'm going to speak with you because you're already there, but Dr. Lorenzo, feel free to jump in if you have any thoughts as well.
This is a really big issue in AI, obviously. There's bias in the data. It learns from the data, and therefore it's kind of holding a mirror up to us and all our biases. I think there's a really interesting issue here, which is that we kind of often only discover ourselves that we're biased when we actually say something to someone and then they challenge it or they talk back to us. And actually, for me, that's the thing we need to understand and build in to the AI systems. I don't think it's possible to always anticipate every possible bias. They're just there. I think the thing that we need to do is create systems that make it possible to be challenged and learn from the challenge and then adapt as a result. And we just don't have that cycle in the current generation of dialogue systems or AIs, language AIs.
Just found that interesting, so I thought I would ask. One more question for you. Well, not one more. This might be of time. Dr. Lorenzo, I wanted to ask you back to your own research. For example, the QMQ project, which is focused on human hand interaction forces. I wanted to ask about, going back to that tactile sensing, what potential does QMQ have for advancing in that field?
So this is I like this project because it also shows another way in which we can use technologies that it's let's say initially developed for robotics, but then we can use it for more cognitive science or human studies, right? Because so I mentioned the use of tactile sensors for robots, so that you put tactile sensor on the hand of a robot, and the robot can understand properties of objects, and it can manipulate objects better. I can manipulate delicate objects to applying the right amount of force, right? And we have worked for many years developing these sensors for the robot. But then we thought, okay, can we use this sensor for another objective? And we created this cube, which is completely covered with these tactile sensors. And then so basically it's a cube, not this shape, but so basically it's completely covered with tactile sensors. So when you take this object, we can measure what are the forces that you apply, where do you put your fingers, etc. So we can use that as a device to study and understand the human manipulation in different settings. So it's, again, a way to use the technology that was initially developed for robotics to actually do human studies. And then the human studies, again, could be something that is directed towards a better understanding of how humans work, but also they could possibly inform how to create better robotic hands or better controllers for the robotic hands we have. So there is, again, this double objective of advancing technology, but also our deep understanding of humans. And we are now using the cube for, initially, I think also with Pat, Pat made the example before of the let's say, how sophisticated it is to pass a pen to somebody else, right? This simple, we call it handover task that are so natural for us, but in fact, there are so many subtle aspects of that we could analyze. And one is, how do we balance the forces from my hand to your hand so that we make sure that the object doesn't fall in the middle and that, we don't have to push it around. So we do it in an amazing, like sophisticated way and like almost without thinking, right? It goes like no problem. But you want to do it with the robot, it's difficult because you still don't know exactly how the coordination between all my fingers between each other and then your fingers, how does that work? And so that's some studies that we are doing with that. But also we are looking at, for example, comparing how do we manipulate an object with our dominant hand, the right hand if you're right-handed, and with our non-dominant hand. How do we apply the forces with the different fingers in a different way? And then we are seeing some initial results that they suggest that basically with our dominant hand, we balance the contribution of forces better. So we kind of apply the same amount of force with each of the finger. With the left hand, we are not so skilled. And so maybe we do what's enough. So, you can also pick an object with just two fingers. But even if we pick with all the fingers, maybe we don't necessarily apply the same amount of force with all the fingers. And in many cases, this is not a problem. But if you have a delicate object, if you apply the same amount of force with all the fingers, it means that overall you apply less force with each finger, so you can be more delicate. And so it seems that these kind of subtle things, we do it naturally, maybe with our dominant hand, and not so naturally with our non-dominant hand. So all these type of studies, they improve our understanding of how we work, how our brain decide those things. And also they can enable better robots.
Good question just popped into my head. Do robots have a dominant hand, or would they both be considered the dominant hand because you're kind of training both? So.
Yeah, no, typically, even in, let's say, many robots, they have only one hand or even just one gripper, so simplified hands. But even the robots that, for example, the humanoid robots that have two arms and two hands, no, we typically don't implement laterality in robot, and they don't necessarily have a dominant hand. So that's an interesting question whether, again, to collaborate with humans in a way that is more legible, like easier to understand and to predict for human. Maybe that could be an interesting aspect, actually.
I just thought it was interesting because my final year project is also on like tactile sensing and myoelectric prosthetics, so that's why I'm especially interested in this as well. So Professor Hewitt, I want to ask you one more time for your own research. You were a former Turing Fellow, and during your time there, it looked like some of your research involved developing adaptive learning for machines. So I wanted to ask about how that impacts the future of communication for robots. Like, how does that adaptive learning, first of all, what does that mean? And then if you could explain a little bit about how it impacts us for the future.
So if I am talking to someone, any of us, if we're in a conversation, when we're speaking, we monitor very carefully how the other person is responding. So if they raise their eyebrows a bit in the middle of what you're saying, that generally indicates they don't understand something about what you said. And you then need to adapt in real time to either use a different word or, check on the understanding or do something in the conversation that allows you to shift your language use. And that's what I mean, at least, about adaptive learning, is that we adjust very quickly to individual differences, to try and make sure that we understand each other. And I think, actually, we know quite a lot about how humans do that. And there's lots of verbal and non-verbal tricks we use to both detect and resolve misunderstandings. And I think that's what we really need to start thinking about in artificial agents, robots, avatars, how they're going to be able to tune in to the particular people they're talking to and adjust their behaviors, adjust their speech, adjust what the word choices are, and even what the meanings of those words are, and how they might shift during the conversation.
Wow. And we're coming up on about 10 more minutes left, so thank you very much for that answer. But I want to just make sure that everybody knows if you would like to ask any questions, the Q&A section is still open, so be sure to ask any questions while we still have these wonderful experts with us. I'll go back to my questions in the meantime, though. So I wanted to ask a little bit more about this AI side of technologies. So how do you think that the AI technologies are being developed and designed with a focus on addressing the human needs? So for example, this need for social communication, like speaking with our hands, or just like being able to talk with different people and seeing their reactions. How do you think that AI is also playing a part in this as well? Sure. I'm kind of directing it to both of you, to be honest.
Yeah, Pat, do you want to go ahead on the communication side, or?
No, you go ahead.
I pick on what Pat was saying before, because I think that's one is a crucial thing but more, I'll take it from the technology aspects, the technology perspective. So it was mentioning this adaptive learning, right? This also in the robotics community, sometimes we refer to it also as a lifelong learning or incremental learning. So the fact that many of these AIs that we have at the moment, they basically learn from a bunch of data, right? You have a bunch of data, you learn your model, and then your model is used and deployed. But it's very useful to have models that can learn incrementally. They can continue to learn. And I think that could, so people also talk about developmental learning. So these are some of the keywords that people talk in the AI field. And that's something that from the technology point of view, from the AI technology point of view, we are still not there yet, as in fully understanding how to realize this type of learning, because it has many challenges. Because basically, you cannot continue to accumulate. You have sometimes to forget something, for example. So to decide, what do you need to forget in order to make space to new knowledge when you want to switch from, one thing that you think to another one, all right? So it's very complex, in fact, in this AI system, but this will really lead to AI system that, they could adapt and they could improve based on the use that we make of them, right? So really it being even more useful to people, because, you will have a certain model that has learned how to do a certain thing, but then you start using this system and it will adapt with you. And it could be just with you, so it could be a personalized kind of development, and so that your own tool becomes better and better over time, or just adapt generally to group of people or community of people. And so I think that is a direction that I think could be it's fascinating, and it could bring AI even more closer to people and really be useful in a lot of tasks, which already is. I mean, I think many of the recent results in AI, they show us how this is changing our lives, and it will keep changing our lives, mostly for the positive, I believe. But yeah, so from the technology point of view, I think this aspect of developmental, lifelong learning could be very important. And this is clearly something that biological agents do all the time, right? And as a kid will learn through their development, through their lifetime, as we evolve also through evolutions at a different time scale, right? So there are all these different ways in which we learn developmentally and really over time.
I'll pause you there. So just a quick question from the chat. If you could give a brief highlight, I'll ask you, Dr. Lorenzo, that's a brief highlight of the difference between the two AI with robotics courses that we offer here at Queen Mary. Apologies to pivot. Just a quick highlight, because we have another question after.
So I think at the moment, this is due to maybe change in next years, but let's say I think at the moment we offer one AI with robotics program in the School of X, which is the computer science department, let's say, the school. And then we have robotics, advanced robotics, or robotics and AI, which is offered by the SAMS, which is the engineering school. I would say maybe the one we offer in engineering is as a little bit more robotics component, while the one that we offer in School of Computer Science has a little bit more of an AI component. But other than that, there is also some overlap in between the two models. So I don't know. I don't think there is a huge difference, but maybe one is a little bit more AI, the other one is a bit more robotics.
I wondered if it might be because you mentioned undergrad and postgrad.
Yeah, I'm talking about the master here. But
I believe they might also be referring to the master. But if not, all the information should be on the website as well.
Yeah.
Just quickly, I'll switch over to the last question from Kanwal, who said, what is your advice to clinicians for adapting and getting familiar with these technologies, especially in underdeveloped countries so that they don't get left behind?
It's not always the case that they're left behind, actually. So, sorry, the example that just came to mind when I read the question was that mobile currencies on mobile phones, that took off in underdeveloped countries before developed. Yeah, I mean, it's a really big practical question. I think we're all actually struggling to keep up at some level, but for clinicians, I guess it's finding access to these very kind of complex and expensive, sometimes healthcare applications. I think at the moment, I mean, Lorenzo might correct me, I think at the moment you would need to find the particular groups that are building those things and then either try to maybe get some online content from them, or, I mean, a lot of the publications are available, you can read about them, but that's not necessarily the same as going to a lab or seeing them live or getting direct experience.
That makes sense. And then just one more question from the Q&A section, which was from Tuan, who asked, which bachelor degree would you require to take the master's degree in AI? Would you recommend computer science or a different background?
I think computer science is a very good background for the AI degrees. Maths, anything that teaches you a lot about formal systems and formal reasoning is a good background.
Thank you very much for your questions, for your answers, everyone. I really enjoyed speaking with you.
yeah, pleasure.
Thank you.
Very interesting discussion.
Pass over to Maria.
Yeah, thank you. Thank you very much for attending our talk today. And I hope you found it as fascinating as I did. And big thank you to Kameron and Professor Healey and Dr. Jamone. I hope you enjoyed today, and I wish you all the best and enjoy the rest of today. Thanks everyone for attending. See you next time. Bye. Have a lovely day.
Bye. Bye, everybody.
Bye now.
Thank you.